Welcome back. Today we will be talking about implicit differentiation. This topic takes some getting used to. It's actually quite simple once you get the hang of it, but it does tend to throw some people off at first. Anyway, here's the basic idea. Up until now, we have been looking at cases in which y is an explicit function of x. And the whole idea of a functional relationship is captured by the functional motto, one in, one out. For every one input you put into the function, you're going to get a unique output, y. But not all relationships between two variables take the form of a function. One of the simplest such relationships would be x squared plus y squared is 1. Well, we know what the graph of that equation looks like. It's the unit circle. And we can see that this is not a functional relationship because if we ask how many values of y correspond to this value of x, the answer is in fact 2. We could have this value up here, which is positive, or this value down here, which is negative. So this relationship fails the one in, one out test, and this is not the graph of a function. Sometimes in pre-calculus classes, they describe this by a so-called vertical line test. If you can draw a vertical line through a graph that cuts it in more than one location, then your graph cannot be the graph of a function, for the reason we just stated. That would mean that for some value of x, there are multiple values of y, and so you do not satisfy the one in, one out condition. If I were to just write down some equation involving x and y, more or less at random, the odds are very slim that I will end up with a case in which y is a function of x. Take this equation, for example. It defines a relationship between its two variables, x and y. There are some points, x, y, in the plane that satisfy this relationship, and some that do not. The set of all those that do is the graph of this thing. And there's no reason why the graph of this thing should look like the graph of a function. In fact, since this is a relatively simple relationship, you have this polynomial in two variables over here, we should be able to see what it looks like by graphing it on whatever your favorite graphing program is. I'm going to pull up Desmos and see what the graph of this thing looks like. And here it is. Strange looking thing, and it crosses through the vertical axis at the origin and at 0, 1. So it's clearly not the graph of a function because it fails the vertical line test. Now that I know the basic shape, let me go back to the blackboard, as it were, and draw a rough sketch of it there. Okay, we have just seen that the graph of this equation looks something like this. Now let's say we wanted to know the slope of this curve at one of these points. Well, you might say, I know what to do. I just need to solve this thing for y, and then take the derivative, and substitute in the appropriate value of x, and I'll get the slope I want. Well, not so fast. This is not the graph of a function, so we're going to have difficulties there. The appropriate value of x is 0, but there are 2 corresponding values of y there. So would we end up with the slope up here, or the slope down here? And those may be different values. Well, this is where the idea of implicit differentiation comes in. Let me go back to Desmos. The idea is that even though y is not explicitly given as a function of x, and indeed isn't a function of x because of those failures of the vertical line test, if I restrict my attention to a sufficiently small region of the graph, so I'm going to zoom in here on 0, 1. That'll do. I don't have to go in any further than that. In fact, to make the point, let me pull this in like that. It doesn't even look like a straight line, but what is visible on the window now really does look like an honest-to-God function of x. There are no visible violations of the vertical line test. And you might say, but I know there's one down below. It doesn't matter. The idea behind implicit differentiation is that I can think of this very restricted bit of the graph that is on the window here as the graph of some function, where I've restricted the range and domain to what is shown here on the screen. So you might say, even though if I extend it out further, there's a violation of the vertical line test, it doesn't matter because I'm not considering that part of the universe. Just this little local region of the point 0, 1. And as long as I restrict my domain to the width of this window and the range to the height of the window, I can forget everything else. And I can say that in the neighborhood of that point, I have y implicitly defined as a function of x. I don't have a formula for it or anything like that. It doesn't matter. And it makes perfect sense for me to talk about the tangent to the curve at that point. Because after all, if I zoom in even closer, restricting the domain and range even more, now my curve is indistinguishable from a straight line. Well, almost indistinguishable. At the very bottom of the screen, you can see them separate. No matter, zoom in closer, closer, closer still. All right, at this point, the original curve is indistinguishable from the straight line, so I can say this is my tangent line. The curve is locally straight. Let me pull back to the original scale. Back, 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 back. Okay, something like that. I know it makes sense to talk about that tangent line, but can I actually find its slope? I can. Let's go back to the blackboard, or tan board, as the case may be. If I'm looking for the slope of that tangent line, I can do this without being flummoxed by the fact that I'm not going to be able to write y as a function of x. The idea behind implicit differentiation is that if I just concentrate on that little window in which y is a function of x, I can proceed as follows. Our problem is to find dy dx at the point 0, 1. I can ultimately find dy dx, which gives me the slope of this curve at any point, as a function of two variables, so that if you tell me the x-coordinate and the y-coordinate, I can tell you the slope of the curve. This is unlike the case of an ordinary functional relationship, where if you just tell me the x-coordinate, I can tell you the slope of the curve there. Here I'm going to need to know the x-coordinate and the y-coordinate, because the x-coordinate of 0 doesn't give me enough information, because there are two different points that have x-coordinate 0 on the graph. Anyway, how am I going to do it? Well, our solution is going to proceed as follows. We will think of y as an implicit function of x, meaning that in this sufficiently restricted neighborhood, y is some function of x. We're just not going to spell out some formula for it. Bearing that in mind, we'll take the derivative of both sides of this equation with respect to x. Let's just write what I said symbolically. Here's our derivative operator with respect to x, and we're taking the derivative of the left-hand side, and of course, we will also take the derivative of the right-hand side, which is particularly simple in this case. So far, so simple. We have an equation. We did the same thing to both sides of the equation, so we still have equality. Now it's carrying this out where we have to be careful. We know we can take derivatives term by term. That's one of our linearity properties. And the first term poses no problem. The derivative of 2x cubed with respect to x is, of course, 6x squared. But now I've reached something peculiar. My next term is minus 4y squared. 4y squared. Yet I'm taking the derivative with respect to x. Notice I am not taking the derivative of minus 4x squared with respect to x. That would be easy. This is 4y squared with respect to x. So because this is peculiar, I'm not going to rush into anything right away. Let me just write down symbolically what we need to do. We need to take the derivative with respect to x of minus 4y squared. This is a place where the Leibniz notation is nice because it helps remind us why this is a little strange. We'll come back to this in a moment. What about the third term? Well, same kind of problem, because I've got an x and a y here. So once again, I'll just symbolically write what we need to do. We need to take the derivative with respect to x of 9xy, whatever that might mean. And this is going to be the crux of the whole thing, these derivatives right here. We'll get to them in the next step. I just don't want you to get lost in the simple stuff. Next term, derivative with respect to x of minus 3x. Well, that's easy because it's just a function of x. We know the derivative of minus 3x with respect to x is minus 3. And what about the last term? Derivative with respect to x of 4y. Well, again, we have those mixed variables, so I'm just going to write down here, we need to take the derivative with respect to x of 4y. And now we go over to the other side of the equation, derivative with respect to x of 0. Well, that's a constant, so of course the derivative is 0. Okay. Hopefully, so far, this hasn't been too confusing. It might seem strange, but nothing too mysterious. We've just used this linearity property of the derivative and gone ahead and taken the derivative in the two places where we knew how to take it. But I've left a lot of unfinished business here. How do I take these three derivatives? Well, the thing to remember is that we are thinking of y as some implicit function of x. I don't have a formula for it, but we can think of it as being out there in some sense. So to remind you that I'm thinking of y as a function of x, restricted to this little blue range, let me change the color of those three y's. to blue. So those are reminders that y is not just some old y. It is some function of x. You could even think of it as y is some function of x. And maybe in the mind of God, this is even explicit. Y is sine of x squared plus e to the such. Who cares? It's just some function of x. And if we bear that in mind, as I said we must do, then we can start to see how we can proceed here. Because each one of these things that we're trying to take the derivative of is really a function of x. Because y here is some function of x. We don't have it explicitly. We're just thinking of it as an implicit function of x, but that's fine. So this is minus 4 times some function of x squared. Well, we know how to take the derivative of such a thing, at least formally. I'll do some scratch work over here to make this clearer. If we had minus 4 times some function of x squared, and we were taking its derivative, which is exactly what we're doing right here, we would know how to proceed. We would need the chain rule, because this is a composition of functions. We have this innermost function, f of x, and then we take the output of that thing, f of x, and we apply this other function to it, the function that squares something and then multiplies by negative 4. So we would just proceed according to the chain rule. Well, if I have minus 4u squared, I know the derivative of that would be minus 8 times u, except instead of the place of u, I have to substitute in my inner function, which would be f of x, and I would not be done. I still have to take the derivative of the inner function. So I'd have to multiply by df dx, whatever that is. Does that all make sense? If it does, then you'll have no trouble with implicit differentiation as long as you are attentive to the details. Let's come back over here and let's concentrate on this first piece. We're thinking of y as a function of x. Therefore, I need the chain rule here. That's what we just did, after all, in our scratch work. So when I take this derivative with respect to x, derivative of the outer gives me minus 8 times something, which is y. I'm evaluating at the inner function, but I'm not done. I have to take the derivative of my inner function with respect to x. Well, of course, that's dy dx. Not too bad, I hope. And note what's happened. Now I have injected dy dx into this problem, which is good because I wanted to find dy dx at a certain point. So I'm glad to see it finally make its first appearance. Let me bring that 6x squared down. Okay, and let's proceed to this one right here. This is all ultimately a function of x, because I'm multiplying 9x by some mysterious function of x, which we're just calling y for now. But it is a function of x. We are thinking of it as some implicit function of x. We don't have access to its formula, but that's okay. What am I going to do here, bearing in mind that this is a function of x? Well, I'm going to need the product rule, because I have a product of two different functions of x, 9x and this mysterious y. So if I apply the product rule, I'm going to get the derivative of the first factor with respect to x, well, that's going to be 9, times the second factor, which just sits there. That's my y. But I'm not done, because there are two terms in the product rule. I have to add to that the first factor just sitting there by itself, 9x, times the derivative of the second factor with respect to x. Well, that is going to be dy dx. Good. I've got another dy dx in there. Well, the minus 3 just comes down, and I still have to take this derivative right here. Well, that's easy. One of my linearity properties tells me that the 4 comes through the derivative operator, like so, and then I'm just left with the derivative with respect to x of y, which is just dy dx. And the 0 comes down too on the right-hand side. Well, now let's think about this thing that I have right here. I originally started with this relationship up here. It was a relationship between x and y. Every point on this curve satisfied that relationship between x and y. Now I have this much more complicated relationship, but it still pertains to all the points on this curve. It's a relationship between x, the x-coordinate, y, the y-coordinate, and dy dx, the slope of the curve at any given point. So I have a relationship between three quantities, and the idea is that if I know any two of them, I should be able to solve for the third. Well, that's exactly what my problem was right here. I knew the x and y coordinates of the point I was interested in, and I wanted to know this third thing, dy dx. That means that if I took this equation and substituted in 0 everywhere there was an x and 1 everywhere there was a y, this would turn into an equation with only one unknown, dy dx, and I should be able to just solve for dy dx and answer my question. And that's not hard to do. Thus, when x is 0 and y is 1, we have, by making those substitutions, this first term is wiped out because x is 0. This second term becomes minus 8 dy dx. This term becomes plus 9 when y equals 1. This term gets wiped out when x equals 0. The minus 3 just sits there, as does the plus 4 dy dx equals 0. And as promised, the only unknown here is dy dx, so we can just solve for it. Well, these guys become 6, and this collapses to minus 4 dy dx, like so, and solving for dy dx gives us 3/2. That is, the slope of the curve at 0, 1 is 3/2, and we are done. Good. Well, I hope you were able to follow that, because if you could, then you understand how implicit differentiation works. And ultimately, the trick was taking this relationship between x and y, between our two variables, and turning it into this relationship between x, y, and the derivative of y with respect to x. This is a technique that is not just useful for finding slopes on curves that happen not to be the graphs of functions, but for a wide variety of problems, which we'll start to look at in the next section of the book, that are usually called related rates problems. More on that to come. But we have more to say about implicit differentiation. What we have done by obtaining this relationship was something that allowed us to get dy dx as a function of x and y. If I knew the x and y coordinates of a point, I could come up with dy dx there. I can actually make that explicit. I can explicitly write dy dx as a function of x and y. Let me alter this problem a little bit. Instead of find dy dx at this specific point, I'm going to say express dy dx in terms of x and y in general, not just at that one point. I'm not going to erase my solution here, or all of it anyway, because a lot of it I can use in this other problem. To get the derivative dy dx in terms of x and y, I still want to think of y as an implicit function of x, and bearing that in mind, I still want to take the derivative of both sides with respect to x. So there's the left-hand side, take the derivative with respect to x. There's the right-hand side, do the same. We carry this out in the next couple of steps. All is well, and only here do I want to start erasing, because I specified to specific values of x and y. So let me get rid of that now. Okay, we still have this relationship between x, y, and dy dx, and my goal was to express dy dx in terms of x and y. Well, all I have to do is solve this equation for dy dx, and that is easy. I've got 3 terms in which dy dx is a factor. So let's just put those in the beginning of the left-hand side, and factor the dy dx out of them. If I do that, those 3 terms become dy dx, their common factor, times minus 8y to give you that term, plus 9x to give you that term, and plus 4 to give you that term. And I still have 1, 2, 3 other terms that do not involve dy dx. And what I'm going to do is I'm going to push them all to the right side of the equation, so that I'll end up with, well, the 3 comes over here, so I get a 3. And the 9y comes over there, be minus 9y, and the 6x squared comes over there to be minus 6x squared. And now if I want dy dx, all I have to do is solve for it. Just divide both sides by this factor right here, and I end up with dy dx is this stuff right here. I have expressed dy dx as a function of y and x, and we are done again. And this form is kind of nice because I could recover what we originally found very easily. In particular, when x is 0 and y is 1, we have that dy dx is going to be this stuff with the appropriate substitutions. And when we make them, we get this stuff. And when we simplify that, we get 3/2 as we saw before. But having this recipe right here makes it easy to find dy dx at any other point on the curve. For example, at the origin. Moreover, when x is 0 and y is also 0, there at the origin, we have that the derivative, the rate at which y is changing with respect to x, is going to be, well, we just make those substitutions. We pop 0 in for x and y, and it's easy to see that upstairs we're going to get 3, and downstairs we are going to get 4. So we will end up with 3/4, which tells us that these two slopes differ. Up here, the slope is 3/2, 1.5. Down here, the slope is only 3/4, 0.75. Let's look back at our better drawn graph on Desmos to see if that looks reasonable. It does. We can see that the slope is clearly steeper at 0, 1 than it is at the origin. All right, and you'll have lots of opportunities in the homework to do problems very much like this. But let's move on to another example. this one not connected to a graph. Given the relationship y(e to the 2y) is equal to x plus tangent x, which you can think of as a set of ordered pairs, or a set of points in the plane that satisfy this thing, express dy dx in terms of x and y. Now, one thought might be, well, I could try to solve this so that I have y as a function of x, and then just take the derivatives as I always have. Good luck doing that. If you somehow could, which, alas, we can't, then we would end up with dy dx just as a function of x. But we've said here that we're content with dy dx as a function of x and y. We can get that by using implicit differentiation, which will turn this relationship between x and y into a relationship amongst x, y, and dy dx. So, our solution. We'll think of y as an implicit function of x, which again just means that whatever the graph might look like, at each point I can zoom in close enough in which y will be a function of x, so long as we restrict our attention to a sufficiently small space. I should actually note that there are some places where this can fall apart. We've said before that differential calculus breaks down at corners, because at a corner point, it doesn't matter how closely we zoom in. Even on an infinitesimal scale, this would not look like a line. It would just look like a peak in a mountain range. Similarly, if I have a crazy curve like this, all is well at almost all of the infinitely many points. But if I happen to look at, say, a place where the curve crosses itself, I'm going to have trouble there as well, because even on an infinitesimal scale, the curve is not going to look like a straight line. It's going to look like two lines crossing, so it doesn't have a well-defined slope. But putting these and other possible caveats aside for now, let's return to the issue at hand. We're thinking of y as an implicit function of x, and bearing that in mind, we'll take the derivatives of both sides with respect to x, so that this relationship right here becomes this one. All I've done is apply the derivative operator to both sides of our original relationship. Now the right-hand side is a piece of cake. We know that's going to be 1 plus secant squared x. This is where it's tricky, but it's not that tricky as long as, once again, you bear in mind that these y's are actually functions of x. I don't know if it helps, but I will color them blue as I did before. Just a reminder, when we see those, we have to think of them as being functions of x. I may not have them explicitly, but implicitly, on some sufficiently restricted window, y is a function of x. Okay, now let's take this derivative. I've got some function of x times this other function of x. It's a function of x because y is a function of x. So the first thing I'm going to need here is the product rule, because I've got a product of two functions of x. And I know that the product rule yields two terms. The first is the derivative of the first factor times the second factor itself. Well, the derivative of the first factor is just going to be dy dx, and the second factor just sits there. On to the second term. Well, I know the product rule tells me that's going to be the first factor just sitting there times the derivative of the second factor. So that's going to be the y just sitting there times the derivative of the second factor. And I'll put that y in blue again as a reminder to myself when I take the derivative. Okay, I'll tend to this derivative in a second, but let's go ahead and write down the derivative of this stuff on the right-hand side, which is a piece of cake, because that is just a function of x. I don't have to worry about y as an implicit function of x over here, because y does not appear. All right, there's only this one derivative left to take. So let me carry the other stuff down, like so, and let's take this derivative. This is a chain rule problem, because I have my inner function 2 times this mysterious function of y, and then an outer function is the exponential function. So I remember how the chain rule works. I take the derivative of the outer function. This is effectively e to the u, and the derivative is e to the u, e to the whatever, but I'm evaluating it at the inner function. So that's going to be 2y. But I'm not done, because I have to take the derivative of the inner function. That is, I have to take the derivative with respect to x of 2y. And I'll pull everything else down. So all that remains is to take this derivative right here. Well, that's very easy, because we know from our linearity property, the constant 2 comes through, and then I'm just left with the derivative of y with respect to x, dy dx. So I can rewrite all that stuff as plus 2y e to the 2y dy dx. And I'll pull everything else down. And now there are no more derivatives left to take. I have gone from my original relationship between x and y and produced a relationship between x, y, and dy dx. So if I want to express dy dx in terms of x and y, all I have to do here is solve this equation for dy dx. And that's easy. I just factor dy dx out on the left-hand side, like so. And now I can solve for dy dx by dividing both sides by this factor, leaving me with this stuff. And I suppose I could clean it up a little bit by factoring out the common factor of e to the 2y on the bottom, which gives me a new denominator of e to the 2y times 1 plus y. And that is about as good as it gets. We have indeed expressed dy dx in terms of x and y. Okay, and there's one last thing I want to show you. We have some old unfinished business that we can finally attend to. Remember those innocent days not too long ago when you took your very first derivative? We learned how to take the derivative of y equals x squared. And from there we built up to bigger and better things. We said, well, it doesn't have to be squared. What if we had y equals x to the n, where n could be any natural number? And we had a very clever argument and showed that the derivative of this thing is, of course, nx to the n minus 1. Pull the exponent down and reduce the old exponent by 1. And we call that the power rule. And we initially only proved it in the case where n was a whole number. But bit by bit we extended it. We extended it to the case where n was a negative number, a negative integer I should say. And then we ended up extending it to the case where n could be any rational number whatsoever. So that if we wanted the derivative of x to the 7/9, well, we knew that we'd just have to pull down the 7/9 and reduce this exponent by 1. So we would end up with 7/9 times x to the minus 2/9. But what if we have an exponent that is not rational? What if we had x to the pi, or x to the e, or x to the square root of 2? Does the power rule still hold in such cases? It does, but we have to prove that it does, and we can do that now. Our claim is that if y is x to the r, where r is any real number, then the derivative of y with respect to x is obtained by pulling the exponent down front and reducing the old exponent by 1. This is the power rule in full-blown generality. And here comes the proof. And you might wonder why it's coming at the end of this lecture. Surely the weirdness of implicit differentiation can't have anything to do with the serene simplicity of the good old power rule. Oh, but it does, and you shall see. If y is x to the r, what are we going to do? If r is irrational, we can't use the previous versions of the power rule, so we'll do something sneaky. We're going to pull this r down to the ground where we can get at it. How are we going to do that? Well, how do we always pull exponents down to the ground when we're trying to, say, solve an exponential equation? With logarithms, because logarithms essentially reduce exponentiation to the simpler operation of multiplication. So let's take logarithms of both sides. Then we can say if y is x to the r, then the logarithm of y is the logarithm of x to the r. And the whole reason I did this, of course, is to use that most famous of all properties of logarithms that tells me that the log of x to the r will be r times the logarithm of x. That seems like a peculiar move. Sure, we got rid of the exponent, but we introduced logarithms. Is that a good trade? Well, this is like watching a chess match, where you might wonder, why did somebody sacrifice a bishop for that? Was that really worth it? This is really worth it, but only when we have implicit differentiation in our arsenal. Because what I can do from here is differentiate implicitly with respect to x. Differentiating both sides implicitly with respect to x yields this. One last time, just to remind you of how this works, I'm going to paint y blue. This is just a reminder that y is a function of x. We are thinking of it as an implicit function of x. So that what I have here is some function of x, whose output I then take the logarithm of. So to take the derivative of all that stuff with respect to x, I need the chain rule. And we remember how the chain rule works. We take the derivative of the outer function. The derivative of the logarithm is 1 over whatever, the whatever being the inner function, y. So I'll have to evaluate at y. But I am not done. I also have to multiply by the derivative of the inner function, here with respect to x. Well, the derivative of y with respect to x is, of course, just dy dx. Meanwhile, on the right-hand side, there's no problem whatsoever. The r is a constant, so it just sits there, and the derivative of the log of x is, of course, 1 over x. Now, this may look like we're just marching off into the darkness, but we are not. Look what happened. We introduced dy dx. We injected dy dx into this problem, and that is exactly what I'm looking for here. So let's just solve for dy dx. To do that, I'll multiply both sides by y, which gives me dy dx on the left-hand side, and r times y over x on the right-hand side. Well, this is good, because now I have an expression for dy dx, and as is usual with implicit differentiation, I've got it in terms of x and y. But in this case, I can rewrite it exclusively in terms of x, because I happen to have an expression for y in terms of x. Simply substituting this in for y will turn all this into r times, and in place of y, I have x to the r over x. But this, of course, simplifies just by basic properties of exponents to r times x to the r minus 1, because I cancel one factor of x from top and bottom. And lo and behold, we have found what we sought. The derivative of y with respect to x, when y is x to the r, for any real number, is indeed rx to the r minus 1, as claimed. And we are done. So a surprise assist here from implicit differentiation in giving us the full-blown version of the power rule. And this tells us now that if we happen to meet in a dark alley the function x to the square root of 2, we can confidently take its derivative, know that it will be square root of 2 times x to the square root of 2 minus 1. And that is all. As I said in the beginning, many find implicit differentiation challenging, so be sure you understand how to do it, because we will need it when we do related rates problems in the very next section. Once you have the idea down, it's pretty easy, but you have to do it several dozen times to get used to it. So now it's your turn to go get that practice, read the section in the book, do the homework problems, and I will see you next time. Goodbye.